Okay, great. I'm presenting joint work with Scott Feld, who is also present, where we've worked out a way to correct for inherent biases in the scale-up network scale-up method. So I'll describe what that method is, um, how we correct for it, and show you some results. So scale-up is a method to count hard to count populations. In absence of a way to systematically survey by using those who know them, essentially. So the process works basically as so. You interview an individual at random from the population and ask them how many people they know in a certain target population that you want to count. Here, I'm taking the example of cocaine users. So how many cocaine users do you know? They estimate from their personal network. Then you ask, well, how many gyms do you know? Some name. And with some idea that they can accurately estimate within amongst the people that they know, how many can they think of? And of course, maybe already coming to mind many biases in this. But a naive way then to scale up is that we know how many gyms there are in the overall population. So you identified 2 cocaine users in your network and 8 gyms. So a naive estimate from this sample of 1 right now is that there are 4 times as many gyms as cocaine users, and we have a basic estimate now for the number of cocaine users in the population. For a larger sample, Kilworth et al. Showed that you basically take an average of this scale up. So for each person, you ask how many cocaine users, how many gyms, you take this ratio and multiply it by, this is this YIT, the number that's how many people I knows in the target population divided by the number that they know in the reference population, multiply that by the known size of the reference population, and average that over your sample. So this has some nice properties. It is the maximum likelihood estimator of the number of people in the target population. Kilworth showed in 1998 that this is unbiased, proved its standard error, so we know, and that you can use actually many reference populations. So you can tighten the standard error by increasing. Don't just ask about gyms, but ask about Marthas and etc. So you ask about a bunch of different known populations, and you can use this to get pretty precise estimates of the size of this unknown population. But there's a rather large issue with this method, which has been addressed in a variety of ways, which is that it ignores the differences in degrees, in average degrees, between the target and the reference population. So let me quickly just explain that. So you might only know 2 cocaine users in your network because many of those whose name you might know, you know all the gyms, but you don't necessarily know all the people in your network who use cocaine. So that the number that could refer them is much lower. So for example, if twice as many people know that a person visits a casino as know that they have a criminal record, the method I just described will be off by a factor of 2. And we can imagine in more hidden populations or in target populations with significantly different degrees, this can be a huge problem. So Solganic et al., and this is sort of one of the general solutions to solving this, is you go and interview the target population and try to understand something. Really you have to survey the target population. Who do you know in the frame population that I'm going to be sampling? So you go and find cocaine users and ask them how many people they know who know that they use cocaine, right? They also need to know about the other person's knowledge, right? So we are proposing a new method which is able to correct this estimate without having to go survey the target population, which is in principle hard. That's the whole point of this method. So that the proposal is to use jointly reported individuals. So we suggest that in the survey, instead of just responding how many gyms you know, how many cocaine users you know, that you can give some information that we can use to identify how often people are naming the same gym and the same cocaine user. I tried to depict that on the right. I don't know how intuitive this is for a sample of 2, but you can imagine a sample of 100. It's sort of like the birthday paradox. You have a higher likelihood of finding jointly identified gyms and cocaine users. So for both the target and the reference group, we determine the number of people reported twice and are able to use this to adjust the estimate. Intuitively speaking, if more are reported twice in the reference population than in the target population, well, this gives information about mean degree. And it's hard to say it a little bit more precisely than that without showing you the equation. So we were able to prove this relationship. So T1 and T2 are how many are reported in the target population and how many people are reported twice in the target population. R1 and R2 are the number of people reported once and twice in the reference population. F here is the sampling fraction. So if you sample 100 people and you know that the population from which you're sampling is 1,000, then this is 0.1. And again, we have sort of the known number NR in the reference population. There is a sneaky assumption here, which is that this ratio is actually involves CT over CR, which is at the bottom. I don't know how clear this is for you, but it's 1 plus V over M squared. So you have to make a distributional assumption about V over M squared. That is that the degree distributions, although they have perhaps very significantly different degree, that they're that this V1 plus V over M squared isn't so different. But I'll talk a little bit more about that later. So there is a natural situation in which the assumption that CT over CR is 1 is satisfied, and that's in the case of a hidden population. So if we're counting a hidden population where the network along which referrals happen, so this is the cocaine users example, the network is the same, but we remove 80% of the ties along which people can refer. Okay, now suddenly the degree distribution, so this V over M squared, is kept constant, but the mean is 1/5. So the estimate that you will get is 5x wrong. So I'm going to show you an example where we just did simulations in a Facebook network. So we have this New Orleans Facebook network of 65,000 people, mean degree 26. We randomly distribute the reference attribute, the gyms, in this population, and we randomly distribute the target attribute, cocaine use, in this population. But only 1/5 of the friends of cocaine users actually know that they use cocaine, right? So we essentially remove 80% of the edges, giving them an effective degree that's much lower. And I can just cut to the chase. Here on the left, we have this Kilworth 1998 maximum likelihood estimator in this situation, as applied to this situation. And on the right, we have our sort of joint report correction, which, as you can see, does significantly better. Seems to be, it is unbiased. And yeah, this is all as should be expected. So I think already here we have an important application where we can change the survey instrument a bit in terms of identifying jointly not reported individuals, and have the ability to correct in a significant way. I mean, this is 4x or 5x, sorry. In a significant way, we can correct this estimate. We did go ahead and probe this assumption a little bit. Okay, but over m squared has to be the same. Well, that's not always true. So we looked at some rather extreme scenarios. For example, what if we want to count individuals with just one friend, right? So here, I probably should have kept the results quiet while I talked about the example, but anyways. So the target population now has variance 0. So this 1 plus v over m squared is 1, and the reference population is still the number of the gyms. And we see, well, the Kilworth et al. Estimate, they don't find many people with degree 1, obviously. So their estimate is, I say their estimate, but the estimate from that equation is incredibly low compared to the true population count of 8,000. Our estimate is off by a factor because of the C T over C R, but it's still on the same order of magnitude, right? So we're estimating 14,000. True was 8,000. That's much better than estimating 300. As another quick extreme example, what if we had a group of, this is 1,500 extremely high degree individuals, and we see something similar, where ours is much closer, but of course it's off by this factor. So that one, you can identify that there's a problem from comparing our method to the Kilworth MLE. So you would be able to see that these are significantly different, so maybe we should be considering that mean degree is significantly different between these groups, impacting the estimate. But two, if we can get adequate bounds on how these distribute, how much can v over m squared even 1 plus v over m squared, can this be so different as to outweigh certain benefits coming from mean degree being significantly different? It seems that the ratio of mean degree can be much different, but this is a sort of an aside. I think this, I put the example again at the end, this example of a hidden population where we can assume it's the same network that people are referring over, but edges are missing independent of network structure. I think this is an important application. So I hope that was clear. We're just, I think, as far as I can tell, this is the first method which is able to use the initial survey instrument in the frame population without going to the targets at all in order to correct this sort of really long-standing issue of mean degree being different in the two populations. All right, well, thank you for your time, and I'll leave, I don't know if I have time, but I'll leave whatever I have left for questions, comments, suggestions.
Okay, since I seem to be awake this morning, unfortunately. So I get this. Practically speaking, though, you would really have to have enough information to know in the frame interview that person A is talking about the same cocaine user as person B or the same gym as person B. Practically speaking, how difficult is that? That sounds tricky to me, but given, setting aside even IRB issues, which would be maybe a nightmare because you have some identifiable data there.
Yep.
Can you share your thoughts on that?
Yeah, so this is certainly future work. Our first thoughts are some portion of the name. So maybe it's the first 2-3 letters of the last name. Of course, IRB is always going to be tricky because this is, by definition, going to be identifiable information. So for first 2 or 3 letters of the last name, first letter or 2 of the first name, maybe some restriction like this paired with our understanding of, based on a census, how common are names to occur. So I think there's also work to be done. Even if they gave us their full name, we would have problem with name overlaps, which weren't actually the same person, right? So there would have to be an accounting for that. But it seems to me that that's possible at this stage. But we haven't we haven't dug too deeply into that, and I think we're trying to present this as like motivational and suggest that the practicality should be thought about carefully. But that's our first idea, I guess.
Okay. Thank you.